In our previous sections, we hinted that there were more formal relationships between V and M. We develop those relationships now in section 8.3. Consider a section of beam subjected to distributed load W of x. Note that W of x is assumed positive downward. Suppose we begin by taking a finite section of beam, delta x about x. Over a finite section, there may be some slight variation in W of x, but we'll eventually be shrinking finite delta x to an infinitesimal dx, so we'll take W of x as constant and equal to its value in the middle of the finite section. Our free body diagram of the finite section has the appearance shown in the slide. We allow the internal loads V and M to vary over the interval by increments delta V and delta M respectively. We now impose vertical force and moment equilibrium. Note again that even though all the internal loads have positive sign convention, we are writing the equilibrium equations in the xy coordinate system shown. Thus, in the vertical force equilibrium equation, the term V plus delta V appears as minus V plus delta V because it is pointing in the minus y direction. Similarly, even though we will quote W of x as positive downward, it also points in the minus y direction and appears as a negative term in the vertical force equilibrium equation. Taking the limit as delta x goes to 0 gives us the differential relationship dv dx equals minus W of x. This tells us that the slope of the v of x curve is directly related to the sign and magnitude of the function describing the distributed load. Similarly, if we take moments about point A of the finite section and again take the limit as delta x goes to 0, we find dm dx equals v of x. That is, the slope of the m of x curve is directly related to the sign and magnitude of the shear force distribution. Think about these results in terms of some of the examples we've covered thus far. We started with some very simple examples involving one or more discrete loads on a beam. Discrete loads are not distributed loads, so in these cases W of x is 0. Our results tell us dv dx is 0, or that v is a constant. Of course, the sudden appearance of a discrete or concentrated load may change the constant, so we would more generally describe v of x as piecewise constant. If v is constant, we also have dm dx is constant, which tells us that the equation describing m of x is just a straight line. If v of x is piecewise constant, then m of x is piecewise linear. Our next set of examples involved uniform distributed loads where W of x was equal to W0, a constant. Our differential relationships tell us that v of x is linear or piecewise linear, and that m of x is parabolic or piecewise parabolic. In fact, we can generalize this pretty quickly. If W of x is described as a polynomial function of order n, then v of x is a polynomial function of order n plus 1, and m of x is a polynomial function of order n plus 2. Note also that in most instances, the slope of v of x is negative because W of x is pointing down, and that direction has already been accounted for in the derivation of our equations. The only instance where this would change is if the distributed load is pointing up, as might be the case, for instance, in the lift under an airplane wing. Because our expressions have been derived assuming W of x is pointing down, the slope of v of x in that case would be positive. dv dx would be plus W of x. We can now construct our expressions for v of x and m of x by integrating these equations. Even though we call this the integration approach, you might note that the equations themselves were derived from the free body diagrams of infinitesimal segments of beams. We might very well call our first approach the finite equilibrium approach, and the current approach the infinitesimal equilibrium approach, but those two very similar names muddle the distinction. We'll just make a note that our integration approach is no less rooted in free body diagrams and equilibrium than what we've called our equilibrium approach. The only remaining issue is to choose between a definite integral, where known values are built into the indices of our integrals, as in xp, vp, and mp in the current slide, or an indefinite integral, where we integrate the expressions, carry along constants of integration, and solve for those constants subject to known values of vp and mp at position xp. There really is no difference between the two approaches, but in the illustrations to follow, I will choose the definite integral approach. The question then is, how do we link xp, vp, and mp to other known elements of the problem? In all of our illustrations, I'll embed the xy coordinate system at the left end of the beam, integrating from left to right as we would any other mathematical function. For this reason, the initial value of xp will be 0. And we have to find the appropriate values of vp and mp that go with it. Let's assume the left end, which we'll call A, has a set of support reactions we'll call FA and MA. So I haven't actually shown any icons for different supports here, but let's suppose at A I have a reaction force FA and a reaction moment MA. Both of these have been drawn in a positive sense. FA is up, positive y, and MA is counterclockwise, positive z. We could again establish equilibrium of a finite segment of width delta x around A, and shrink delta x to 0. Were we to do that, we would find that V tends to plus FA and M tends to minus MA. The difference in sign stems from the different sign convention we chose for V relative to M. If we have a pin or roller support, there is no ability to react a moment and MP becomes 0. If we have a built-in support, then a moment will be reacted and MP is non-zero. If there is no support and simply discrete loads at x equals 0, as in some of our initial cantilever beam examples, then the values of Vp and Mp take on the appropriate values of those loads. For instance, in our first examples, we had a single discrete force P pointing down at x equals 0. Then Vp becomes minus P and Mp becomes 0. So let's suppose we have established our initial set of Vp and Mp for xp equals 0, and we're integrating along x. At some point, we may encounter discrete loads, either forces or couples. Here we'll consider just a discrete load of r in the plus y direction in one case, and just a discrete couple of plus c in the z direction in the other case. Note that both of these discrete loads are represented in the positive coordinate directions. In these sketches, the notation minus and plus as subscripts on V and M indicate the values of internal loads just before, in the case of minus, and just after, in the case of plus, the discrete load. Equilibrium of a segment including the concentrated load tells us that the jump in shear force distribution is plus R with no discontinuity in bending moment in the one case, and also tells us there's a jump in bending moment of minus C with no discontinuity in the shear force in the second case. Again, the difference in the sign of the jump is due to the difference in sign convention between V and M. Now let's take a look at some examples to see what's involved in practice in using the integration approach. In example 1, we have a problem from section 7.4. The distributed load is a linear function of position. The reactions at B are provided, but we really don't need these except as a check after the fact. There are no discrete loads between A and B, so we should be able to construct V of x and M of x in one pair of integrations. The origin is a free end with no discrete loads, so we have xp equals 0 inches, vp equals 0 pounds, and mp equals 0 inch-pounds. Using our previous notation, we make use of the fact that xp is 0 and that vp is 0, to get this result for V of x. This is easily integrated and we're evaluating this between the limits of 0 and x. One thing to watch out for is being careful to include this lower limit. When we begin, we're beginning from xp equals 0, and in the case of a polynomial like this, there will be no term from that lower limit. But generally, as we move through the beam, xp may not always be 0, and we have to remember to include the evaluation of that lower limit in the integral. For now, this just turns out to be minus 4 pounds per inch times x plus x squared over 20 inches. For the moment equation, we once again make use of what we know about xp and mp, and since we now have v of x, this is just the integral from 0 to x minus 4 pounds per inch times the quantity x plus x squared over 20 inches dx. This again integrates easily. Between these limits of 0 and x. Again, in this particular case, the lower limit doesn't give us anything, and so m as a function of x is just minus 4 pounds per inch times the quantity x squared over 2 plus x cubed over 60 inches. Note again that we simply inserted w of x as it is here. We didn't have to put in a negative value for w of x because our derivation assumes that w of x is going down, and so we simply insert it as it is into the expression. Since w of x is a linear function of position, we obtain a parabolic expression for v of x and a cubic expression for m of x. As a check on our results, we evaluate v and m at x equals 20 inches and should find a match between these internal loads and the reactions at b. At x equals 20 inches, we find v equals minus 160 pounds. The sign convention for v is such that this corresponds to a force pointing in the plus y direction. So v matches b sub y as we move to the end of the beam. At x equals 20 inches, we find m equals minus 1333 inch-pounds. The sign convention for m is such that this corresponds to a clockwise bending moment. So m matches the moment reaction as we move to the end of the beam. This consistency provides confidence in our results. Note also that we can get a sense of the shapes of these curves even without the explicit functional dependence of these expressions, because we know that w of x provides the local slope of v everywhere, and v provides the local slope of m everywhere. Both curves begin at 0 because of the free end of the beam. The v of x curve has a modest but non-zero slope at x equals 0 because w of x is non-zero there, minus 4 pounds per inch in this case. We know from visual inspection of w of x that v of x will become progressively more negative because its slope is becoming more negative as we move from left to right. At the end of the beam, its slope has increased to minus 12 pounds per inch. M of x begins at 0, but its slope there is also 0 because v is 0 at x equals 0. Again, m of x is expected to become progressively more negative because its slope is determined by v of x, which in this case falls monotonically from a to b. In this example, we have a beam loaded with a single off-center force in P. The beam is pin supported at A and roller supported at B, so we could begin by finding the reactions for the beam. If we were to do that, we would find that the vertical reaction force at A is 2/3 P, and the vertical reaction force at C is 1/3 P. This problem is sufficiently simple that we should be able to write down v of x by inspection. Because there is no distributed load, v of x is piecewise constant. It starts at x equals 0, equal to the vertical reaction at A, 2/3 P, is constant until B, and then drops down by external force P to minus 1/3 P. It remains constant until the end at B. The bending moment distribution is piecewise linear and a little more complicated. The pin at A supports no moment, so MP equals 0. Integrating our constant v of x gives us m of x equals 2/3 p of x. This holds between x equals 0 and x equals L over 3. At L over 3, our moment doesn't change, but its slope does. The value of the moment at x equals L over 3 as we approach L over 3 from below is 2/3 p times L over 3 equals 2/9 pl. For x greater than L over 3, we use our same expression, but now have to be aware that xp and mp are different. xp now represents the transition point of L over 3, and mp takes on the value it did as we approached L over 3 from below, 2/9 pl. V of x is now minus p over 3. Here's where we have to be careful about our lower limit. As a check on what we've done, we should again find a match between V and M as they approach C and the reactions at C. V is minus P over 3, which is consistent with the vertical force reaction there. M goes to 0 as we approach C, which is encouraging since the roller can't support a moment reaction. The severity of the kink in the moment distribution is directly related to the change in V as we move through the discrete force at B. As can be seen in the figure, the m of x function has a positive slope equal to 2p over 3 as we approach L over 3 from below, and a negative slope of p over 3 as we pass through L over 3 and head to C.